So electromagnetic phenomena applied in many engineering field and technology, and there are many different types of electromagnetic problems. As a consequence, during the past 60 years, starting from the mid-60s, people have developed many numerical methods to solve those diverse electromagnetic problems. In essence, computational electromagnetics can be categorized into two families. One is to solve Maxwell equation in the frequency domain, and the other is to solve Maxwell equation directly in the time domain. So these two families are coupled to each other through Fourier transform, and the reason why researchers in electromagnetics want to solve Maxwell equation in the frequency domain is that the effective dimensionality of the method in time domain and frequency domain are different because of the way we formulate those methods. In frequency domain, Maxwell equation represent 3D problem. In contrast, time domain Maxwell equation represent a four-dimensional problem. So as a result, the degree of difficulty or complexity of solving Maxwell equation in the frequency domain is significantly reduced. And the frequency domain calculation depends on the size of the problem in terms of the wavelength. So if the problem size is very large, then of the wavelength, then we can use a so-called asymptotic, or we can say it's a high frequency method. So this method can be divided in turn into two groups. So one starts from geometrical optics and geometrical theory of diffraction, and then a uniform theory of diffraction. And the other group of asymptotic methods starts with physical optics, and it's called physical theory of diffraction. And there is also a technique called incremental length diffraction coefficient. So we divide these two groups of asymptotic methods because for historical reason they were developed separately. There are other cases of electromagnetics problem, and they occur when the size of the problem is comparable with the wavelength, or when we want to have a very accurate solution. Sometimes we need to have an accuracy that cannot be afforded using asymptotic method, and in these cases we have to solve Maxwell equation directly. We also use methods called first principle based method. So within this family of methods, we can solve Maxwell equation directly as partial differential equation using either finite difference methods or finite element method. And today, finite element method is a dominating mathematical method. And this belief that in the frequency domain of finite difference method offer no advantage at all in solving Maxwell equation. If we use a green function or convert the partial differential equation to integral equation, then we have a method of moment, and the method of moments reduce fully populated matrices, and researchers have developed a whole set of fast algorithm to handle the algorithm based on the method of moments efficiently. There is a family of fast algorithm that can be used to speed up the method of moment matrix solution. Okay, and in turn, now we can discuss time domain method. And again, we operate in the framework of partial differential equation, and then the most popular method is a finite difference time domain method, often abbreviated FDTD. A lot of researchers like this method because it's straightforward, at the same time very compelling. One can learn this method in a very short time, and as a result, one can very quickly write computer code and get approximate solution to the problem of interest and understand the electromagnetic phenomena behind the problem. A finite difference time domain method doesn't involve the solution of linear algebraic equations, and because of it, this method is the most efficient. As I mentioned earlier, the finite element method is most common used for frequency domain problems, and in contrast, for time domain problems, the finite-difference time domain method is the most popular. However, to model geometry more accurately, to be able to use conformal measures, in recent years, researchers developed a finite element time domain method. So there is also a discontinuous Galerkin time domain method, and for those who do research in computational electromagnetic, look at some new directions to cause it discontinuous Galerkin time domain is one good method to explore. So conventional discontinuous Galerkin method from a class of numerical method for solving differential equation, and they combine features of finite element and a finite volume framework. Particular discontinuous Galerkin method receive considerable interest in problems with the dominant first principle parts such as electromagnetics and fluid mechanics. Discontinuous Galerkin time domain method is a relatively new method, and it's much simpler method than finite element method, and it offers much better potential in terms of handling computational problem and in terms of multi-scale tasks. So much like the continuous Galerkin method, the discontinuous Galerkin method, the finite element method formulated relatively to weak formulation of a particular model system. But unlike traditional continuous Galerkin method that are conforming, a discontinuous Galerkin method works over trial space of functions that are only piecewise continuous. So also a discontinuous Galerkin time domain method has been developed to handle multi-scale problems. So this method has recently been implemented in numerical software, other commercial packages, so they become more opportunities to explore features in practical cases. There is also a family of computational methods based on integral equations, such as the integral equation time domain method and others. And also, there are quite a few problems in electromagnetics such that none of these numerical methods are advantageous to other methods, and we combine this numerical method to solve so-called hybrid using hybrid techniques. In such cases, we can focus on the advantages of different numerical methods and discard the disadvantages to achieve better, more efficient solution. And another aspect is the domain decomposition approach. In this case, we can efficiently parallelize this numerical method on the parallel computer system to utilize parallel CPU systems and even a GPU system. So not only practical experiments, but of course also theoretical modeling as well as other aspects often play important role in development of solution applicable to real world problems. And because of the linearity of Maxwell equation, analytical tools have helped and carried out development of electromagnetic technology. And for long time, theoretical modeling in electromagnetic perform the abundance of analytical tools valuable. An analytical solution often correspond to realistic problems in the real world. So earlier theoretical models in electromagnetics have a lot of examples of demonstration of mathematical skills of researchers. So the most known examples of this are a Rayleigh solution to the waveguide problem, solution of Raleigh's scattering by small particles, the Murphy solution to the half-plane problem and half-space problem, Mie-series solution to scattering by sphere, and several scattering solutions by canonical shapes documented by Boltzmann and many others. So because electromagnetics was predated by the theory of sound and fluid, so much of the mathematical development of sound and fluids can be used in electromagnetics with some enhancement to account for the vector nature of the field. However, leaps and bounds progress in computer technology open up new possibilities for solving electromagnetic equations more accurately for theoretical modeling, and it can be applied in many practical cases. So this is essentially when the structure is complex, and instead of being driven by quantitative engineering, where physics is needed, then we can use computational method for electromagnetics to do the design. And the use of computational methods in electromagnetics can be reduce our dependence on experimental test. So that's also save some resources and time. And computational method in electromagnetics also the large part of physics of electromagnetic equation when they're solved, and it can present a high fidelity virtual experiment quite close to the real world. So almost any method can be made to do anything, but the real question is what the particular method is best for. And here in this course, we place greatest emphasis on addressing the question of what the methods are best suited for and how to minimize force feed. So the method can usually be expanded to a broader class of electromagnetics problem, and it just won't be efficient or it's not often used. And that's why we need to look for more efficient method.